For such a simple instrument, the magnetic compass can behave in, well, let's call it some pretty unexpected ways. Even a small speed change or shallow bank is going to throw it off. And the FAA handbooks just scratch the surface on why this actually happens. So if compass errors still feel like a mystery, this video will make them click. Hi, I'm Greg from Pilot Institute, the online ground school that makes aviation easy. And I'm going to show you why the compass errors can lie to you and what to do when it does. But first, we need to understand how this all works. And to do that, we've got to start deep inside the planet. 1,800 miles beneath our feet, swirling molten iron in the Earth's core is going to create a magnetic field, basically turning the entire planet into a giant magnet. In general, magnetic field lines stretch from a magnet's south pole to its north pole. Earth works pretty much the same way. The lines are going to curve from the magnetic south pole to the magnetic north pole. And here's what some very smart people figured out over 2,000 years ago. If you let a bar magnet spin freely, it will line itself up with those invisible field lines. Why? Because opposites attract. The magnet's south pole is going to point towards the Earth's magnetic north pole. And that's all of a compass really is. But to make it useful in the air, we need an actual heading. So to do that, the magnet is attached to a rotating card marked like a compass rose. It shows cardinal directions, north, south, east, and west, and headings in between, usually in 5 degrees increment. And as the airplane's heading changes, the magnet keeps pointing towards the magnetic north, causing the card to rotate. A mark on the compass face called the lubber line is going to show you current heading. Simple enough, but here's where things can get a little tricky. For the compass to work properly, it needs to stay roughly parallel to the Earth's surface. That's why it's mounted horizontally, either on the glare shield or near the top of the windshield. But instead of looking straight down at it, you're actually reading it from the backside. And that changes how the compass card is laid out. If it were printed like a regular compass rose with north at the top, then on the heading of north, you would actually see S under the lubber line, and it would look like you're actually flying south. So to fix that, the compass card is rotated 180 degrees. Now from the pilot seat, it shows the correct heading of north. Problem solved, right? Well, kind of. Flipping the card fixed the heading issue, but now the compass rotates in the opposite direction of the turn. Let's say that you're flying north and start a right turn to 090. You'd expect the compass to rotate right with you, like the heading indicator, but it actually rotates left. And if you turn back to north, it rotates right. Now this can be disorientating at first, but check out the description. There is a link to a compass card that you can print out at home or just use on your phone. It can really help you visualize how this works. One end of the magnet is labeled NP for north pointer. That's the end that points to the magnetic north. Now if the Earth's magnetic field were the same everywhere, the compass would be a lot easier to use. But nature doesn't make things that simple. So let's see what happens when the magnetic field starts working in 3 dimensions. It's tempting to picture the magnetic field running along the Earth's surface like lines that are drawn on a map. But it doesn't really work that way. At the magnetic equator, the field lines run parallel to the ground, so the magnetic force is completely horizontal. But as you move closer to the poles, those lines start to tilt, adding a vertical component. Now the compass only uses the horizontal part of the field in order to determine direction. At extreme latitude, the vertical pull gets too strong and the compass becomes unreliable or even completely unusable. But in the mid-latitudes where most of us fly, the field has both a horizontal and a vertical component. And here's the issue. That vertical pull causes the magnet to tilt downward, a behavior that we call magnetic dip. The compass is actually built to resist that tilt, but dip still causes some unusual errors. But before we get to them, I want to talk about something else. It's called inertia. Even if you're not familiar with Newton's law of motion, you actually already understand the concept of inertia. It's an object's tendency to resist any changes in motion. Now imagine that you're enjoying a cup of coffee while you're driving. If you suddenly hit the gas, the car moves forward, but the coffee wants to stay where it is. So it's going to slosh backward, hopefully not in your lap. That right there is inertia. And as you're about to see, it's one reason your compass can be trusted, even in level flight. So let's take a look at acceleration error. And just to keep things simple, everything we're talking about here is in the northern hemisphere. If you're flying south of the equator, the compass is going to behave the same way, but in reverse. Okay, Here, we have an airplane flying straight and level on a north heading. If we add power and accelerate, what happens to the compass? Well, nothing happens. It's going to stay fixed on north, no errors at all. And if the airplane slows down, well, again, nothing happens. Alright, let's try the same thing now, but on an east heading. This time, when the airplane accelerates, the compass is going to swing slightly towards the north. And if we decelerate, then it's going to swing towards the south. So why does that happen on some heading but not on others? Well, let's go ahead and take a look inside of the compass. The compass card itself is slightly bottom heavy in order to help it stay level. But because of inertia, it's going to resist moving right away. So when the airplane accelerates, the card is going to lag slightly behind. That makes the aft end of the card, the side that's closest to you, tilt upward. Now the card here is no longer level, it's angled forward, creating a low point in the front. Now on an easterly or westerly heading, dip is going to pull the north pointer slightly downhill towards the low point, and that deflects the compass to the north. This is a great time to use that compass card that we mentioned earlier. We're going to start with an easterly or westerly heading. Tilt the back of the card up, and then you'll see that the north pointer is going to take the shortest path downhill, rotating the card clockwise towards the north. But the closer your heading gets to north or south, the more the magnet is going to be aligned with the field. And there is less sideways pull in this case, therefore less error. Okay, now let's go ahead and see what happens during deceleration. This time, the aft end of the card is going to tilt downward, and the north pointer rotates towards you. Since the pointer is opposite the S on the card, the deflection appears as a turn towards south. The easiest way to remember this, ANDS. Accelerate north, decelerate south. This error really only happens while your speed is changing. Once you stabilize, the compass is going to settle down again. But acceleration errors is really not the only way that dip can throw you off. Now let's go ahead and see how the compass can lie to you when you start to change headings. When you bank the airplane, you're also banking the compass. Now magnetic dip doesn't just pull straight down, it also pulls sideways. And that changes how the compass is going to respond. It might lead, it might lag, or briefly show the wrong direction. Now we call this turning errors. And it's not the turn in itself that causes the error, it's actually the bank. That's why you won't see this happen when you're taxiing around on the ground. Got that compass card handy? Well, let's go ahead and use it in order to see what really is going on here. Set up a right turn from a heading of north. Now the card is banked to the right. Now you'd expect the heading here to increase, but that's actually not what the compass shows, at least not at first. In the bank, the dip is going to pull the north pointer slightly downhill towards the Earth. On the north heading, that rotates the card clockwise, opposite the direction of the turn. Same thing with the left bank. The card should rotate towards the west, but dip is going to pull it towards the east. Now we've got a problem. The horizontal part of the magnetic field, the part that actually gives you direction, is fighting with the dip. And at first, the dip is going to win. When you roll into a bank from a northerly heading, the compass initially shows a turn in the opposite direction, then lag behind the actual heading. But the further you get from north, the weaker the effect becomes. When you pass through east or west, the compass reads correctly again. On those headings, there is no sideways pull. Now let's try a left turn from south. This time the dip pulls in the same direction as the turn, but it pulls too much. The card rotates faster than it should, and the compass leads the turn. Again, the error goes away as you pass east or west. So turn from a northerly heading will lag, turns from a southerly heading will lead. These turning errors make it tricky to use the compass to hit specific headings, but there's a technique that makes the compass usable outside of straight and level flight. And yes, it comes with another memory aid, UNOS. Undershoot north, overshoot south. Now, if you're turning to a northerly heading, you need to roll out early, and if you're turning to the south, roll out late. But how much should you under or overshoot? Well, there's actually a rule of thumb for that. Take half of your latitude and then add 15 degrees. So if you're flying at 40 degrees north, half of that is 20, plus 15 is going to give you 35 degrees of correction. Now that's the maximum adjustment from a turn directly to the north or to the south. The closer you are to east or west, the smaller the correction needs to be. Let's walk through an example. Say that you're turning right from south to north. At first, the compass shows a faster turn than you're actually making. From a southerly heading, the compass leads, we've looked at that already. As you reach west, your actual heading and the compass are going to match up. But as you approach north, dip starts pulling the compass in the opposite direction. So when the airplane is actually heading north, the compass is lagging behind. That's why you undershoot. Using a 35-degree correction, roll out when the compass reads 325. After it settles, the compass is going to show north or pretty close to it. Same idea if you're turning back to south, just overshoot by 35 degrees instead. It doesn't really matter which way you actually turn. So from a left turn, roll out at 145 degrees. From a right turn, roll out at 215 degrees. It's really satisfying to level the wings and then watch the compass kind of settle right onto the target. It just takes a little bit of practice. Flight simulators actually do a great job at modeling the dip errors. But there's one error that's actually more frustrating in real life, and it's called oscillation error. Because the compass card has to pivot freely, things like turbulence or even abrupt control input or even engine vibration can make it swing and bounce. That makes the compass tough to read accurately. And of course, unless it's your own stick and rudder skills that are shaking things up, just average out the reading the best that you can. Now this next one is not really a compass error, but it can get you way off course if you forget about it. Take a look at this map. The geographic North Pole, the one that's at the top of the globe, is not where the compass points. It points to the magnetic North Pole, which is about 1,300 miles away in northern Canada. And here's the problem. Aeronautical maps, like sectional charts, are based on true north. These vertical lines right here, they're called meridians or lines of longitude, and they pass through the geographic pole. And when you plan your flight, you align your plotter using those lines. So how do we convert a true course into a magnetic course? Well, we're going to use something called magnetic variation. That's the angle between the true north and the magnetic north. But of course, it can be that simple. Variation is not constant. It changes depending on where you are. That's why on sectional charts, you're going to see what's called isogonic lines. That's this dashed line right here. Each one of these shows the local variation in degrees and whether it's east or west. So for example, here in Prescott, Arizona, variation is 10 degrees east. So magnetic north is 10 degrees east of true north. Now over here in Cleveland, Ohio, it's 8 degrees west. And near Minneapolis in Minnesota, the poles are pretty much aligned, so variation is 0. Now to convert from true course to magnetic course, you're going to use this memory aid right here. East is least, west is best. Subtract east variation and add west variation. So if your true course is 050 degrees and variation is 8 degrees east, subtract it to get a magnetic course of 042 degrees. And if variation is 8 degrees west, add it in order to get 058 degrees. And on a calm, windless day, flying that magnetic course on your compass is going to take you to your destination, right? Well, not necessarily. There's one last compass error, and this one's entirely man-made. Magnetic deviation happens when the magnetic field inside of the airplane interferes with the compass. Electrical systems, radios, metal parts, anything that creates a magnetic field can throw it off. And there's no way to eliminate that interference completely. And it means that the compass might not actually match your actual magnetic heading. And that's why airplane compasses have what's called a compass correction card. It shows the difference between what the compass reads and your actual magnetic heading. So for example, this card right here says that a compass heading of 090 matches the actual magnetic heading. So in this case, no correction needed. But to fly a magnetic heading of north, you'd need to steer to 355 on the compass. That's a 5-degree deviation. And it may seem like a small error, but over a very long flight, it can actually add up. So before you fly a compass heading or sync up your heading indicator, check out the deviation card first. Alright, if you've been following along with that little compass card, keep it handy. It's a great tool for review. And if Check Right Prep is on your mind, I've got something else for you. Our free private pilot study sheet. It breaks down all the essential topics like navigation, airspace, weather, and many more into one easy-to-use guide, and it's completely free. So just click in the link in the description to download it, and thanks for watching. I'll see you in the next one.